We're now going to study related rates. Related rates are essentially word problems where we use the chain rule and implicit differentiation to decide how various rates of change, derivatives, are tied to one another, are related to one another. This is most easily seen through examples, so let's jump right in. Imagine a car that's driving north from this point here. So this car is heading up and up and up and up and up. There's an observer sitting, meanwhile, 150 meters away from where they started. So we can imagine the configurations would look something like this. Always 150 meters down here. Then the car goes further north. And then the car goes further north still. Even further than that north, like that. And in all those scenarios, the 150 meters remains constant. Now we're interested in a few things. The car is traveling at a constant speed of 20 meters per second. Okay, we have a velocity. The question is asking how fast is the distance between the observer and the car changing? All right, we can see from these little sketches that if we gave this a name, D, it's going to change over time. When time is close to 0, we'll have a distance just a little bit longer than 150, and then it's going to get longer and longer and longer. Now, how can we tie that rate to the only other rate that we know, the 20 meters per second heading north here? The easiest way to do that for most application problems like this is to find something that's true all the time, and then use that all the time true equation, differentiate it, and solve for what you want. In this particular case, it might help if we introduced another variable here, which would be the length of this side. We'll call it y of t, because it's sort of like a y coordinate. What we know is that dy dt is equal to 20 meters per second. What we want is the rate of change of this distance here with respect to time. So something that's always true between y and d is a Pythagorean relationship. We have a right-angled triangle here, 150, y, and d. So it's always going to be true that whatever y is, if I square it and add 150, I'll get that distance to the observer from the car squared. So that's straight Pythagoras. Once we have that, we can bring in our idea of implicit differentiation and find the rate that we want. We want how fast that would be a time derivative of the distance. So what we're going to do is take the time derivative of both sides. If we do that here, we're going to get the derivative of 150 squared plus, I'm just going to write it now as y squared and d squared. And of course we need that derivative still. And here's where we see the implicit differentiation really shine. The rate of change of 150 with respect to time, well, it's constant, so we get 0. The rate of change of y squared with respect to time is 2y, but how is y changing with t? It's changing as the derivative, dy dt. Likewise, on the other side, the derivative of anything squared is 2 times the original function, and because d and t are separate variables, we get the time derivative here of that distance. Taking this equation to the next page, we can start solving for what we want, remembering that dy dt, which is the rate of change of this side of the triangle, is going to be 20 meters per second. Having copied over the equation, we can remind ourselves that we know dy dt is equal to 20 meters per second, and that what we want is the rate of change of the distance to the observer from the car. And we can sub those in. So we'll have 2y times 20 equals 2d times dd dt. Okay, so we're almost there. We have this. In fact, what we could do is divide through by 2d here, and we could say that the derivative of our distance with respect to time, or how fast something's moving away, would be 20y over d. But what are these values? Well, there was that last piece of information, the when in this scenario. Let's go back one page. We want to know how fast is the distance between the observer and the car changing after 10 seconds. That's the key thing for us. So at 10 seconds, we could get complicated and fancy, or we can just recognize that we're starting at a y value of 0, straight in line with the observer, and we're going for 10 seconds at 20 meters per second. So y at 10 seconds will be 200 meters. And if y is 200 meters, we can draw the triangle, 150 on one side. We just calculated 200 on the other. And if you look carefully, this is a 3, 4, 5 triangle. It'll be 250, or you can use Pythagoras if you prefer. And that'll give us the last distance. So at the particular instant we're involved with, that we're curious about, we would have y equal to 200, and d, the distance to the observer, being 250. We can now plug those in here, and we'll get 20 times 200, that's our y, over 250 equals the distance, or how fast the car is moving away from the observer. And we can simplify that a bit. That's 4/5. That would be 80/5, or better known as 16 meters per second. The car is moving away. At 16 meters per second from the observer. So it's worth thinking about, does that make sense? Does it not make sense? The speed here is 20, it's certainly in the right realm. And the question is, do we expect it to be lower or higher? In this case here, it turns out a bit lower just because of the mathematics. But you should ask yourself, does that make sense on a more intuitive level? And that concludes our first related rates example.